Hello everyone, welcome to another class of the course on quantum theory of many-body systems in condensed matter. My name is Luis Dias da Silva, and today's class will discuss many-body quantum systems in the first quantization. Remember that in the last class we talked about single particle systems in the first quantization. We talked about the harmonic oscillator, talked about basis states, and today we're going to extend these concepts to any particle quantum systems. And let's give an example of two particles in the harmonic oscillator, and there will be an assignment regarding the helium atom. Okay, so let's see what you get today. So here is an example of an n-particle Hamiltonian. We can write it as a sum of two classes of terms if you want. So first comes the single particle operators, so it's a sum from I going from 1 to n of a kinetic energy and a potential energy. Each of these are dependent only on the canonical coordinates of a single particle, either the position or the momentum. And last class we talked about Hamiltonians of this type. So the single particle Hamiltonians, as we mentioned. If you haven't seen the class, I'll try to remember to put a link over here. Now this term arises from two particle operators. So these two particle operators, they involve the coordinates, or perhaps the momenta, of two particles at a time. One example is interactions, say electron-electron interactions, or electron-proton interactions, which will involve both the coordinates of the electrons, the two electrons, or the coordinates of two protons. So all these two particle operators, they come in here, and here the sum runs from I and j equals 1 to n, with I different than j. And I included this factor of 1/2 here to discount for the fact that when I is, say, 3 and j is 4, this sum will include a two-body operator at positions R4 and R3 as well, because the sum runs independently. So these two terms, VR3 and R4, for particles 3 and 4, is the same as VR4 and VR3, which is also included in the sum, but you have to, is just equals to VR3, R4. So we need these factor of 1/2 to discount for this double counting. Sometimes you might add 3 particle operators or 4 particle operators, but in condensed matter is not as common as in, say, quantum chromodynamics, where you might have 3 particle vertices and things like that. Here, for the most part in this course, we'll restrict ourselves to 2 particle operators, namely Coulomb interactions. That's our focus. And as we shall see, this will already be hard enough for us. Notice that this sum accounts for the interactions between every particle in the system with every other particle. So you have many more terms of 2 particle operators than you have of single particle ones. Okay, so let's continue. Last class we defined then the representations that we're going to work. We're going to use Dirac's notation, and in many cases we'll bring it to the configuration space with R, this should be 2, sorry. R going from 1 to n, so because we have n particles, we have 3n coordinates, right? 3 of these. In principle, these are all 3D, but of course we're going to restrict ourselves to 2D and 1D at a times. And this cat represents a n-particle state. And as usual, we have a bra related to the cat, which comes from the complex conjugation of it. And of course, we can define an inner product between these two n-particle states. The same, very similar to what we did for single particle states. Now, what happens is that this integral is going to run over the entire configuration space. So this psi here will run, it's a n coordinate function, and this one is as well. So this inner product is defined as that. So it's of course much more complicated to work with n-particle states. But if you want to say the time evolution for the particular state is also given by Schrodinger's equation, just essentially the same. Remember, this is an n-particle Hamiltonian, this is an n-particle state, and everything works as before. Now, how about a basis set? In the last class, we defined that for single particle states. We mentioned that it could be coming from the eigenstates of a given operator, say a Hermitian operator. Sometimes it's very useful. And here, we might as well construct our n-particle basis out of single particle basis. How do we do that? We say that we have a basis set for a single particle basis, say the eigenstates of a single particle Hamiltonian. If I want to create an n-particle state, I can take n single particle states, and do a tensor product between them. That will give me an n-particle state. Remember, the first state will represent the first particle, this is the second particle, all the way up to the last particle, capital N. And so I can combine the basis set n times to construct a basis set for n particles. And we're going to see a couple of examples in a bit, but let me just say that if these guys are orthonormal or orthogonal to each other and they form a complete basis set for single particles, this guarantees that this basis will also be orthogonal and will be also a complete set. And hopefully they are also normalized in the sense, right? We're going to see that sometimes this is not enough, especially if you have identical particles, but this is a way to build at least your single particle state or your n-particle state. And as such, if you have an generic n-particle state which is time dependent, you can expand this in this n-particle basis as well. And as before, the coefficients, these C coefficients, and here we're using a representation where the time dependence is encoded in these coefficients, they will be given by this inner product between your basis state and your ket, your psi state, the state that you're interested on. Now, we can also use, as before, the full spectrum of an n-particle operator. Say, if you know the full spectrum of an n-particle Hamiltonian, this will also form an n-particle basis. The thing is that this is much harder to do. Sometimes unless you know by beforehand what is the spectrum of this guy. For instance, in cases where this is made out of single particle states, just single particle terms of single particle Hamiltonians, then you might construct the spectrum, and therefore you might construct the basis. But in this case, you essentially fall back into this other one. But I just wanted to leave it here because this is not the only way to build a single an n-particle basis. You might get it out of the spectrum of an n-particle operator as it's written here. Moving on. So far, if you noticed, let me go back a little bit. Try to go back here slowly but surely. I allowed here in our single particle terms for the masses of the particles to be different, right? This would mean that you can tell which particle is which. So you say you have a three-body system of three particles, say an electron, a positron, and a proton, and they are, well, the positron has the same mass as the electron, so it's not a good example. Let's say an electron, a muon, and a proton, right? And they are all interacting with each other. This would be a system like that. So you have three particles, each with its own mass. But the more interesting case for us in condensed matter is the case where you have n identical particles, say 3 electrons, right? With the same mass, and you cannot tell one from the other. So in the first case where you have the electron, the electron, the muon, and the proton, you can distinguish them. So they are quantum particles, but they have different quantum numbers, right? They might even have different masses or different charges, and you can differentiate them, right? This is what you call a system of distinguishable particles. And you can differentiate the particles by performing measurements and tell which one is which. So the electron is doing that, the muon is doing that, and the proton is doing that, right? They might even form a compound state, right? But it's made out of distinguishable particles. But it is more interesting if you have a system of n identical particles where they have the same observable quantum numbers. They're indistinguishable. So they might have the same mass, the same charge, same spin. And in this case, you cannot tell which one is which. You cannot perform a measurement to tell which one is which. Essentially, they have the same observable quantum numbers. So a system of n electrons with the same spin, so they're all spin polarized, or sometimes we call them spinless, is an example of that. They are in the same quantum state, same energy, same everything. You cannot tell which one is which. Now, in these systems of identical particles, if you cannot tell one from the other, and they are all in the same quantum state, that means that they should have the same probability density if you exchange two of them. Why? As I said, if the particles are all identical and you cannot distinguish between them, say if you have the state, they are all in state phi, on any-body quantum state, and you project that state in configuration representation, so you have the coordinates of the n particles here. That means the absolute value squared of this state at this time will give you the probability density of finding the particles at each of these positions. Particle 1 at position R1, particle K at position RK, particle M position M at position RM, and etc. Now, if you cannot tell the particles apart, it means that if somehow you would measure a similar state, but two of the particles have switched position, say this particle here, which I'll label K, is now in position Rm, and while particle M is in position RK, something like that. In this case, you cannot tell which one is which. So let's go again. You have these two particles, K and M, and now particle K is in position Rm, particle M is in position Rk. You cannot tell these two probability densities from one from the other. It means that they have to be equal. If they are equal, it means that the actual wave function has to be the same up to a global phase, right? The absolute value squared is the same. It means that this has to be different from each other only up to a global phase. And more importantly, and this is also an experimental fact, is that if I go back and exchange the particles again, so that the kth particle comes back to position Rk and the mth particle goes back to position Rm, I get another phase which is exactly the same. So this is an experimental fact, that a second exchange of the same particles brings the state back to the initial one with no phase difference. It means that, the phase that you get for exchanging the particles, first, it does not depend on which particles you pick, right? Because if you do a series of exchanges and you go back to this original ordering, right? Particle K, position Rk, particle M, position Rm, you get the overall phase should be 1. It means that if you do then twice the same operation, you get this phase squared. You would have to e to the I theta squared equals 1. It means that these phases not only are the same, but they can only be either 0 or pi. And that's quite remarkable. It means that you only have two types of particles in nature in 3D. They're either bosons, what you call the particles where when you exchange two of them in a quantum system, the state of the system goes back to itself with a plus sign here, so e to the I0. Or there are fermions, where you get a minus sign whenever you exchange two particles in the quantum system, the position of the two particles. Now, in 2D, and we're going to discuss that towards the end of the course, there is the possibility of having phases which are not 0 or pi, but somewhere in between. So these are called anyons, and is a very hot research topic in condensed matter now. We're going to talk about Majorana bound states and things like that. So keep in mind that what I just mentioned to you is valid strictly in 3 dimensions. And in 3 dimensions, yes, you only have either bosons or fermions, as far as I know, right? But, so yes, this is, again, is remarkable, because it's a symmetry of nature, in a sense, that tells you that this phase is fixed. Right. Okay, so let's start with a couple examples now. So say that you have two particles in the harmonic oscillator. We discussed the harmonic oscillator last class for the single particle states. We diagonalize this Hamiltonian. We construct a basis set, and now let's say that we have two particles, one in coordinates x1 and p1, so momentum and position and momentum, and a second particle with coordinates x2 and p2. So this Hamiltonian is just a sum of two single particle Hamiltonians, which are identical, same kinetic energy and same one body potential. But we have two of them, so this is truly a two particle Hamiltonian. I could have an interaction term here, and we might play with that in the assignments. So let's see what we get from this. So the spectrum for the single particle states we know is the spectrum for the harmonic oscillator. And then we have the spectrum for each of these two operators. They in fact have the same spectrum because these are indistinguishable particles. They have the same mass, same frequency, right? Same harmonic oscillator, so these energy sets are the same. And we can use the single particle states, the single particle basis, to construct the two particle basis states, right? So as we mentioned before, this is just the first step is to produce these states, which are essentially the tensor products between cats of particle 1 and particle 2. Now I'm keeping this label 1 and 2, but later we'll drop it. And the convention is that the order of this tensor product also gives you the label of the particles. So the first state in the tensor product relates to particle 1, the second to particle 2, etc. But I'll keep that for now until we get more used to this notation. But in principle, what I'm doing is just a combination, right? I take this and take this with this, gives me one base state, one single particle, two particle base state. This with this one with that, this one with this, and I keep going, right? So I have m states in the bases. I'll have just m squared bases here, base states here for two particle. Okay. Now let's see what we get out of this once we go into the coordinates and exchange of particles, if we get what we should. So let's go into position representation, and we know how to write the single particle states in position representation. This will give me the wave functions for the harmonic oscillator, which in real space are Hermite polynomials. And now the question is, what are the two particle basis wave functions in position representation? For that, let's bring up our blackboard here, and I'll try to remind you how do you get, say, a state that is a tensor product of a one state. As I mentioned, I will drop the index here in these notes. So this is particle 1. So this single particle state for particle 1, and this is single particle state for particle 2. Now let's build another two particle state of which is an eigen, x1, x2. This is also a two particle state. It's something like that, right? Notice that this is particle 1, this is particle 2. Don't look much at the labels here. It could be something else. It could be, I don't know. Let's write this x what? x30, x3, and x4, right? Just to confuse you. this would be x3 and x4, but this is only a two particle state. So this is still particle 1 and particle 2. There's no particle 3 and 4. What this means is that I'm talking about a cat that particle 1 is in position x3 and particle 2 is position x4. This could be anything, right? So just keep that in mind, because this might get pretty confusing pretty fast. All right, now what I want to calculate is to project this guy into these positions here. So this is what I want to calculate, right? And how do I do that? Well, I do something like this. Inner products of tensor products. This N1, N2, oops. And then this guy X on this one, and this one X on that one. So this is going to be X1 N1 times X2 N2, and in the notation that I had, that this is phi N1 X1 phi N2 X2. Now this is now a complex number, so this is just a product. So it doesn't matter if you change the order here, right? But sometimes we prefer to keep the order the same, right? As the order of the tensor product here. So that we know that, okay, we're talking about particle 1 here and particle 2 here. So this is particle 1, and this is particle 2. So this might get things confused a little bit, because but we can take from the indices here that this is particle 1. All right, particle 1, particle 2, and particle 1. So yeah, let's try not to get ahead of ourselves. Okay, let's go back to the slide. So this is what I just did. I just wrote this basis states in position representation. So now we can try to see what do we get from exchanging the particles. Okay, so the question we want to ask is this. Is this basis appropriate to describe indistinguishable particles? So this is the basis, the two particle basis we created, correct, out of the single particle states. And we know how to write each one of these in position representation. The question I want to ask is this. If I take this state, 1 and 0, right, and I write it in position representation, x1 and x2, and now I exchange the positions of these two particles. Do I get the same state up to a phase, and this phase is plus or minus? Okay, that's the question. So let's go back to our blackboard. So let's say that I have now this phi2. Oops, sorry. There. So let's do a phi2 here. Let me, oops, through Z. Alright, I want to just show this a little bit. So phi2 which is, as we had in the slide, described like this, if I'm not mistaken. Yes, that's right, 1 and 0. All right. So let's write this in coordinate representation, right? This is phi. It is not too good. Phi 1 at position x1, phi 0 at position x2, which is precisely what we had here, right? Okay. Now, this is psi 2 of x1, x2. Now we want to exchange these two guys. I want x2, x1. And as I mentioned before, I'm perfectly allowed to do that, right? This will give me phi 1 and x2. This is still particle 1. Notice? This is still particle 1. Particle 1. And phi 0 at position x1. Oops. Go back here. And this is phi 2 with the positions exchanged. x2 and x1. All right. Now this is the exchange, right? I can do it here, or I can do it here. And this is clearly different than this one. It's not just plus or minus different. It's really different. You're calculating, say, a Hermite polynomial at position 1 and multiplying it by a Hermite polynomial, another Hermite polynomial at position 2 plus prefactors. Prefactors would be the same, but now you're multiplying this Hermite polynomial another position times this calculated another position. This will give you different numbers. So this is truly different, right? Meaning that this basis, as I wrote it, doesn't account for particle exchange as in the sense that I need these two states to be related to each other in this fashion. They have to be either plus or minus one another. So the conclusion that we get here is that they're not. And that means that this basis is not appropriate to describe indistinguishable particles. And that's a problem, because if my Hamiltonians are for indistinguishable particles, I should get a base states that would allow for that, at least, right? So how do we solve this? Well, the thing is that we have to adapt our basis, essentially force it to obey the correct exchange rule. So if I'm talking about bosons and the particles, the two particles in my harmonic oscillator are bosons, then I have to have a symmetrized basis, so that when I exchange two particles, I get the correct plus sign on there. So let's go back to our example here. So what do I get here? So I need then this. I need a symmetrized basis. Symmetrized, let's call it 2. x1, x2, which has to be normalized and everything, but has to give me the same thing when I exchange the particles. Right? So how do I do that? One possibility is to do this. I combine these two guys. Right? I come here and say this. All right. So I'll take the old phi2 at x1, x2 and add the phi2 at x2, x1. Oh, okay. All right. So let's do, yeah, this is this and this is this. They're of course different. So now if I put a 1 square root of 2 to normalize, but let's make it more clear here that these are exchange coordinates. So this is 2 and this is 1. So that will give me, this is of course is going to be equal to F2 as when I exchange the particles, right? I'm just going to write over here big parentheses there. Because if I exchange the particles here, this one goes into that, this one goes into this, and everything is the same. What if I want to have an antisymmetric combination? I'll just put everything in yellow, which is minus. Put this minus here. And phi 2 antisymmetric. So this is for bosons. And this is going to be for fermions. So I can do the same trick, right? I can define this guy like this. Phi 2 x1 x2 minus phi 2 x2 x1. Yeah, all right. So this will give me minus phi 2a x2 x1, right? Because this, when I exchange the particles, this one goes into this one goes into this, and there will be a minus sign here. So it's going to be minus this. So this is for fermions. All right. Then this is a symmetric. This is, I call it S because it's symmetric under the exchange of the two particles, and this is antisymmetric under the exchange of the two particles. All right, let's go back to the slide here. So I can do that with all these basis states here, right? 0, 0, 1, 0. So these two, I have to combine them into one. This one remains, and so on. For fermions, this one is not allowed. Why? Because there's no way I can antisymmetrize this one when both functions are in the same state, right? So this one is simply not allowed by symmetry, by big statistics, as we call it. So I can only have the antisymmetrized version of the other ones. And now you notice that here the number of basis states which are constructed this way is smaller than the number of basis states here in the original basis. So in a sense, I am restricting the Hilbert space to only those wave functions, two-particle wave functions, which have this property. They're either symmetric or antisymmetric respect with particle exchange. Okay, so this is a very important point, that when you look here, the states which obey this rule is a subset of the total number of allowed, say, Hilbert space states for two particles. This is fine for distinguishable particles, though. Okay, so if I have not two electrons or not two identical particles, this state is okay, still okay, but not if I have identical particles. So when I do that, I symmetrize or antisymmetrize them, then particle exchange is well defined, and I get wave functions that describe either bosons or fermions. Okay, so this is an important point. All right, so there's this other question that we sometimes get confused, and this is definitely confusing. Okay, what about other quantum numbers? So I gave an example of a harmonic oscillator with a single quantum number, essentially the n, right? What happens if I have something like the hydrogen atom, which has more quantum numbers? You have spin, you have angular momentum, you have the z component of angular momentum, you have all that. So how do you go about and construct a many-body basis out of a basis like that? So the rule is, there are a few ways to deal with it. One, which I consider to be more pedestrian and simple, is that you count a single particle state for every time you have one combination of quantum numbers, right? For instance, if you have a principal quantum number, angular momentum quantum number, z component of the angular momentum quantum number, spin quantum number, you have 4 here. Okay, each combination of these numbers will give you one index alpha and only one. So 0, 0, 0 up is 1 alpha, 0, 0, 0 down is another alpha, 1, 0, and then you keep labeling your states, and then you use these ones to construct your many particle basis, right? That's I think a nice and consistent way to do it. Another one that we might talk a little bit about is to construct, say, two particle bases out of algebra of, say, adding angular momentum, for instance. Say you're adding, so say if you have two single particles like this is definitely a two-state, two-particle state, but you can rewrite it in a multiplet. You add the angular momentums here, and you get also one state which is a two-particle, but it's just a different combination of this with, say, the other m's and the other sigmas. In a sense, it's a change of basis from what it done here. This is trickier, but is sometimes useful to construct these multiplets. Okay, but for the most part, this this way is okay. And this is the way that you're going to, I'm suggesting that you use in the assignment. So there are other ways, but let's stay with this one. So this is the assignment for today's class. I might include another one regarding an interacting harmonic oscillator. I'm still writing it though, so it's not going to be here in the video, but I might add into the assignment, and of course we can discuss it in class. So, but for now, this is the assignment. Let's consider a model for the helium atom, where you have a Hamiltonian which has two single particle Hamiltonians coming from, which are the hydrogen bases, right? This is essentially the hydrogen atom Hamiltonians for particle 1 and for particle 2, or for electron 1 and electron 2, plus an electron-electron interaction term, which is given by this guy. This is definitely a two-particle state. So the first thing I wanted you to do is, let's write a basis, right? The basis is going to be in the non-interacting case, when only the Hamiltonian is just the sum of H1 and H2. And I'd like to write the ground state for this Hamiltonian, H1 plus H2, in position space. And then tell me what the energy is. So the energies of the hydrogen atom you should know. If not, take a quick look at a Wikipedia, but keeping that in mind, that is especially ground state. What is the ground state? The energy of the ground state of the hydrogen atom in electron volts. This is something you should, I don't know, tattoo in your palm or something, right? Because people will in competitions here in Brazil, in the concursos, this is something that gets asked a lot, for instance. So tell me what's the energy for the two-particle state for the non-interacting case, and also write down the matrix elements, the integral. No need to solve it, just write it. For the matrix elements for the two-body operator, the electron-electron repulsion in this basis. And this actually, if you calculate this integral in electron volts, this is going to give you the first correction to the ground state energy of the helium atom. So this is a good quantity to know. So I'm giving you the radio wave functions for the hydrogen atom. And if you have any questions, we can discuss it in class. All right, so that's it for today. In next class, we're going to talk about second quantization. See you there.